All right, line A5, learning task 1, characteristics of three-phase AC. By now as an apprentice, you should have probably run into a couple of three-phase systems. If you've only dealt with single-phase systems so far, this is going to be completely brand new. But for those of you that have dealt with the three-phase systems, what we're going to go over this next week and a bit is going to really put into perspective some of the systems that you have been working on. First of all, the need for three-phase systems. If you take a look inside of that first paragraph over there, it talks about that these are used for generation, transmission, and distribution of electrical power. By far and large, we're going to find that throughout the province. There are places where we have single-phase distribution, but anytime that we're looking at massive industrial complexes or a lot of work or a lot of power that's got to go out, we're usually going to go and have three-phase, and then we'll tap down to single-phase past that. The reasons for three-phase are listed, some of the better ones down below over here, but the first one, possible to create smaller machines with the same kVA capacity, so we can get the same power out, we just get a much smaller package, which also means it's going to be much cheaper because there's going to be less materials that are going to be required for that. The next reason, we have better distribution systems. We can distribute more power using less copper. Once again, all of our copper and aluminum costs are high. We want to stay away from that. Third, a three-phase system is going to go and produce peak voltages that are going to be spaced apart. So it's going to be a bit of a more even type of power distribution. We're going to get smoother operation out of a lot of our machines. On a single-phase machine, anytime that the motor is running, we're kind of have this bump, 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 bump. And it's very similar to if you had a flywheel going and you would just give this thing a slap every once in a while to continue this thing moving. On a three-phase system, we still have got these bumps, but the bumps are much closer together and they aren't as much of a difference between where it's slowing down to where it's speeding up. We just get a smoother operation. We're going to see that once we take a look at some of our three-phase waveforms. Last of all, the design of three-phase motors, not transformers, but just motors, is going to be much simpler than single-phase motors. We've got a lot less gear that needs to go around. Basically, it's just going to go and be copper. We don't have any connection in a lot of our motors going from the stationary part, the stator, over to the rotary part, the rotor itself, which means we don't need brushes, slip rings, or any of that other gear. We also don't need to have start windings, capacitors, things like that that do cause problems on some of our single-phase systems. So we're not going to use, single phase where we can go and get away with three phase. If there's three phase available, it always makes more sense to go and use the three phase components. Let's start by taking a look at how we generate the three phase voltages. The first thing we're going to take a look at is Fleming's left-hand rule. This is all the way back from first year. It's not inside of your binder right now, but it's something that you should be familiar with, and it's where you're going to go and use your three digits, your thumb, your first finger, and your middle finger to go and figure out your different directions. Thumb is going to be thrust, is what we're going to go and look at. The first finger is going to be field. Note how there's an F for field and an F for first over here. And then the center finger, or the middle finger, but we're going to call it the center finger, is going to be for current. So we just have two C's, center and current, two F's, field and first, two T's, thumb and thrust, that we are going to go and use to associate these. As long as there is thrust, that means that there's going to be motion relative between, so it could be motion on the conductor or motion on the magnetic field. We're going to generate voltage. We also have to have a direction of the field that we're going to know. So this finger is going to be pointing from north to south. And then that's going to tell us the direction that the actual electrons are going to go and flow along through our circuit itself. Go back to your first year material if you're unfamiliar with this, or look up some YouTube videos. It's a pretty common thing that gets dealt with in a lot of different places, but you need to be familiar with it before we can take a look at our three-phase distribution. Three-phase distribution is going to be what we refer to as a polyphase system. It's any system that has got two or more phases. There are two-phase systems. There are four-phase systems. We don't use them here in BC. We're going to go and use single-phase, or we are going to go and use three-phase. Any other specialty phase systems are just going to be done inside of specialty pieces of equipment. So we're just going to completely ignore them for now. First thing that I do want to note about this is that we have got our stator, our stationary part of our machine over here. The stator has got the actual copper conductors that are going to be laid out inside of it. We're going to try and keep the copper stationary. And then inside of that, we have got our actual magnet that we're going to be rotating around. And we can see that we've got a magnet, therefore we have got a field, we got the F. We see that we have got rotation, that's this arrow over here. Therefore, we have got thrust, and because we have got those two, we are going to be able to go and develop that C, or that current flow that we're going to go and get off of this thing. I should note as well that sometimes we're going to go and have stationary wires with a rotating magnetic field in the center. Other times we could have stationary magnets with a rotating set of wires. That's much less common because once again we'd have to use slip rings to take the power off of the rotor. So this is what we're usually going to go and see. The next thing that I do want to note is that there's axes inside of here. I see that my C winding goes to there, my B winding goes to there, and my A winding goes to there. Physical location on the machine is a very big thing because the physical location is going to go and choose when we are going to go and have a peak. We know that we get a peak anytime that we're cutting through the maximum number of flux lines, which is going to happen right directly at our pole. In other words, when this north pole is directly lined up with this C section over here, we are going to go and get maximum current through C. But as it moves away from C towards B, we're then going to get maximum current across B, but less current across C. Let's take a look at how those currents actually go and develop. Over here, we have got a set of windings that are shown. We also see that we have got our rotation, north-south, and our thrust that we are going to go and have on our conductors. Remember that going back to this over here, the thrust is always looking at the motion of the conductor. And if our conductor is moving in one direction, if the conductor is moving in this direction, it's the exact same thing as if we had the field moving in the opposite direction. So when we go back to this over here, we see that we are moving the field, which is the same as if our thrust was going in the opposite direction. For my thrust on all of these, since I have got the field moving in this direction over here, therefore my thrust on the conductor is going to be in that direction. We can use our left-hand rule now because we have got two distinct quantities that we are going to go and have. We see that we've got our flux, that's going to be our north to south lines coming out like that. We see that we've got our thrust, that is going to be in that direction. So what you need to do is you need to start with a finger gun. You're always going to start with a finger gun. You're going to keep your middle finger folded down like a good polite human being. And you're going to go and have your first finger and your thumb that are going to go and follow these two arrows. You're going to align your thumb with the T that we have over here. You're going to align your first finger with the arrow that we have there for the field. And when you do that on your left hand, at that point, once you've got those two lined up, you should then be able to stick out your middle finger at 90 degrees to the rest of these, and you see that your middle finger is pointing in towards the page over here right now, which is awesome because that means that, I'm just going to erase some of this over here, that means that my current is heading into the page, and we see that by the fact that we have got the dot and cross convention over here. Going back to dot and cross, if it's been a while since you've gone through that, dot and cross is basically looking at either end of a conductor, and you can look at them as if there was an actual arrow traveling through them. We'll stick some feathers on that end, we'll stick an arrowhead on this end. If the arrow's coming towards you, you're going to see the point, you're going to go and see a dot. If the arrow is traveling away from you, you are going to go and see an X, or you're going to go and see the fletches traveling away from you. And so we see that inside of here because we just used that left-hand rule. The other thing that I want to note is that these windings are connected all the way through. Let me just get to my marker over here. What we're seeing off of this is that my A line connects all the way through to the other A. That's those dotted lines in the back there. So going back to this over here, I see that right now I am going to go and have on my A line over here, that conductor is, I'm just going to dot it through, connected across to the other side like that. So my current is going to be traveling through that conductor like that little arrowhead that we just drew there before and coming out on the other side. And we see that that lines up with this side over here where we have got that dot on the system itself. Okay, this makes sense for my A conductor. If I take a look at my A conductor then right now, I can see that I'm going to be getting a voltage that's going to be generated off of my A conductor. The next question is, well, how big is that voltage going to go and be? And we know that there's a couple things that are going to define the value of voltage. That's going to go and be Faraday's law, Eg is equal to BLV. You should have this one memorized. which means that my voltage generated, that's this EG, is equal to my flux density. Let's write that. My length of conductor, and then my velocity that I'm going to be taking my conductor and moving it through the magnetic field, or my field through the past the conductors. We've got all of these the same for all of our windings. If you take a look at your windings themselves, we see that the windings themselves should all be constructed with the same length. This would make even voltages, and they should all have the same velocity because this magnetic center pole over here is rotating, so they all have the same relative velocity. The only thing that is going to be different about them all is going to be their beta, or their flux density, that we are going to go and have. And the beta, I'm just going to erase those there, is going to be determined by how thick that magnetic field is going to be. Going back to first year stuff again, we know that our magnetic field is going to go and come out and go around. It's going to leave from the north, come back to the south. And it's always going to be densest right at the very top of that pole. From there, it's going to start to fringe, we call it. We're going to get these weaker and weaker lines that are going to be going around. And if we take a look at these weaker and weaker lines, we see that those weaker lines are actually going through B and C as well. But we see that the number of lines that we have going through the A section right over here and coming back to this A section over here is going to be much greater than the number of lines that we have going through the B's and the C's right now. Which means that the one that's got the greatest amount of lines is therefore going to go and have the greatest flux density. And if it's got the greatest flux density, it therefore follows that it's going to go and have the greatest value of voltage. And so we're going to take a look at that right now on this point A of the graph. I'm just going to erase that so we can take a look. Point A of our graph over here is going to be this A phase right over here. And we see that A is at a positive peak right now for its direction. I'm just tracing right over, but we're looking at this point right now. It is at a maximum positive over here. And I see that B and C are not at a maximum value. They're partially through. I see that my C phase, that's going to be this one over here, C is falling, and I see that my B phase is rising back towards the positive again, but that they're not at the absolute peak values that they could be at. And that makes sense because they have fewer lines of flux. So right now, A is peaking, B and C are not going to go and be peaking. The other thing that I do want to note as well about this alternator right now is that my A's, my B's, and my C's, if I divide this whole thing in half across the north and the south over here, I am always going to go and see that all my directions of current are going to be the same. I'm going to have all of my tails over here on the left-hand side. I'm going to go and have all my heads over here on the right-hand side, where all of those currents are going to be coming out right now. The big difference right now as to why I've got A as my positive, and we see that my A is in my positive direction, and my B and my C in my negative directions, is that I have got over here on B and C, my subscripts are different. And the big thing we're going to look at is I've got a big uppercase over here, and I've got a lowercase. Uppercase, lowercase, uppercase, lowercase, going around the outside of this, which means that I'm going to go and have ends. We're going to take a look at those ends and how they generate values of voltage later on. But this relationship that I see right over here, where these are both on the lower side of the graph compared to my A, which was up on the upper, is all to do with the way that I have connected my lowercase and my uppercase. I don't know, that's not a highlighter right there. My upper and my lowercase letters over there. So we're going to get to those connections afterwards. Right now, we're just going to go and continue to rotate this alternator, this magnet right over here, through. And as we rotate this thing through, we see that the next thing that it is going to line up with is going to go and be my C over there. Let's take a look at what that looks like. If I go and rotate it through to my, hold on a second here. This thing is absolutely crazy right now. The drawings inside of here are showing my rotation, jumping around all sorts of directions. That's all right. We can work off of any one of these. I was hoping it would be stepwise, but that's just the way it is. Over here, we see that the next one that is going to go and be peaking over here is going to go and be my B. And once again, we're looking at the maximum amount of flux density that is coming out of the pole and entering into the pole on the opposite side. And we see that that is aligned with my B winding here. Because it's aligned with my B winding, we're going to go and get maximum value on my B winding, and my voltages for my A and for my C windings are going to go and be at minimums and in the opposite direction. They're going to be smaller because there's less flux going through them. And we carry that on into our third position that they show over here, which is where C is peaking. And I see that my C is peaking once again when I have got my pole lined up with the winding over here. And it's therefore going to be lined up with my winding on the opposite side as well. So we are going to go and have a C peak off of, once again, beta, length, and velocity over here. All of that ties together. We get those high values of voltage right now on the C winding, and we see that A and B are going to go and have a smaller value of voltage in the opposite direction over here. One other thing that I just want to note about all three of these drawings is that I'm aligning my north pole every single time with the lowercase lever. So lowercase a results in a positive A voltage. I align my north pole with a lowercase b, which results in a positive B voltage. I align my north pole with a lowercase c, which results in a positive C voltage. So we're always looking at aligning this north, which is this lowercase letter. Now the letters are arbitrary in a sense, you know, they're just put on there by whoever does the windings, but then we are going to make these connections to go and cause us to get a proper rotating three-phase voltage. And the way that we're going to do it is we're going to go and take these windings, and right now I've done what's called a representative drawing. This isn't the way it actually looks. The windings are wound all in circular fashion around the outside of the motor, but if I were to go and separate them and think about them just as if they were point sources of voltage, I could draw something that looks like this. And you'll note that I've got my lowercase a and my higher case a. My lowercase c, my higher case c, my lowercase b, my higher case b, all of these are represented inside of here, and I see that I'm going to go and have 120 degree separation. This 120 degree separation is literally the same separation that we had on the actual alternator itself. If I take a look, I see that I've got my A line. Let me just go and delete that one there a second. If I take a look at my A line, I'm just going to draw this through as an arrow, starting at the lowercase, going to the uppercase. I see I've got an arrow that looks like that. On my B, starting at the lowercase, going to the uppercase, I see I get an arrow that looks like that. And starting at my C, on the lowercase, going to the uppercase, I see I get an arrow like that. And what I can do is I can take all three of these arrows out and I can just draw them together. Now what happens is we get something different. If I take that C arrow out, I'm going to be able to draw that C arrow down like that. And then if I'm going to go and take the tail of my C, I'm going to go and tie my B to that. So if I tie my B to that, I would see that my B tail goes up there, little b, oops, sorry, little b. Let me just erase that one because it's a total mess now. And then last of all, if I take my A, I would see my little lowercase a going out that way. A to my uppercase A. And this is where we're developing these values of voltage themselves from. We're always looking at the references, the ABC, over here they're drawn as windings, but it's really going to be values of voltage that are going to be peaking 120 degrees apart. The other thing that you need to remember is that when it deals with AC, how many degrees are there in a complete sine wave? Oh yeah, I can't hear you guys, but there's 360 degrees inside of a complete sine wave. So if we go back to one of these drawings over here, we'll just go back to this one. And if we were to go and take a look at my A, we'll just highlight over top of the A, like that, that there would be 360 degrees. 360 degrees divided by 3 equals 120 degrees. And if I take a look at this length over here and I divide it into three different positions over here, what I'm going to get is I'm going to get one that's going to be right over here, and I'm going to go and get another one that is going to go and be right over here. These lengths, that's a third, that's a third, that's a third over there, are going to go and correspond with where I see each of my voltages themselves starting. Right over here, I see A starts over there, 120 degrees in, B starts 120 degrees in, C is going to go and start. They're 120 degrees positioned out of line from each other. What we can do with these windings, once we've got these windings set up, we put them into the alternator, alternating uppercase, lowercase, all the way around. What we can then do is we can go and make two main types of connections. The first connection that we are going to go and have is this one over here, which we are going to go and call our Y, or sometimes people will just go and call it the Y type of connection. And it's called that because it looks like a Y. What we're going to do is we're going to take all of our lowercase letters, we connect them together inside of the machine, and we only take power out on the A, the C, and the B uppercases. Three leads that are going to come out, and we're going to have a Y connection. The other one that we're going to go and have is a delta connection. And the delta connection is also represented by this triangle. This triangle is actually Greek letter D, or delta, the fourth letter in the alphabet. We see it inside a code book as well. We use it to represent change quite often. Delta can be representative of that. But we call this the delta connection because if we take a look at it, the entire setup over here looks as if this thing were a triangle. Once again, we're going to go and have connections from component to component. We take a look at my uppercase A winding. I see that it connects to lowercase b. So uppercase A to lowercase b. Uppercase B goes to the next letter, lowercase c. Uppercase C goes back to the first letter, lowercase a over there. And we're going to go and take from this whole setup here as well, three leads out of our machine, our A, our B, and our C windings, which is where we're going to get those three-phase windings. Y and delta have each got unique characteristics and specialized applications for them. We're going to look at all of those in a couple of lessons from now. All right, the next thing that we have to do is we have to talk about scalars, phasors, and vectors. You should remember all three of these terms from previously. Scalars are things that have magnitude only. Magnitude. My vectors have got magnitude and direction. And then my phasors have got magnitude, direction, and rotation that are all going to be tied together. Because it's a three-phase system, we're actually going to go and have rotation. It's as if the peak of A, B, and C, it's going from one to the next as we go all the way through, which means that we are going to go and have continuously moving voltage. That would be an absolute pain to analyze. So what we're going to do is we are going to go and take our phasors, these magnitude directions that have rotation, and we are going to go one at a time. We're just going to go and lock them down. And we're just going to take snapshots in time, and that way we can look at all of this stuff. So understand that it's always rotating, but we're only looking at it as if it were small snapshots. Okay, a couple of different conventions that we need to go and talk about for these. The first thing that I want to do is I want to go and take this entire drawing over here. Let me just remove all of that. And I want to go and draw in the background of this thing some coordinates. You guys remember this from level 2 and from basic math. We're going to go and have quadrant 1, 2, 3, and 4 over here. These are mathematical graphing quadrants. We know that we have got x's that are going to be horizontal. This is going to be my positive x direction. This would be my negative x direction. We're also going to go and have y coordinates. This is going to be my positive y. This is going to be my negative y directions over here. We're going to do all of our work around those basics, around that whole quadrant type of system. We're just no longer going to draw the quadrants into the back of everything we look at. But what I do want to go and take a look at is the fact that this whole upper section, let's erase all of that, this whole upper section is in a positive y, and this whole lower section is going to go and be in a negative y. So positive y, negative y type of state over here. The direction of our rotation is always going to be, if we're looking at a positive direction of rotation, would always be starting from this 0 over here and rotating all the way around to the opposite side. We would go 360 degrees all the way around. We can look at negative rotation as well if we go from 0 and we go around in a clockwise manner like that, but that would be negative rotation. We don't usually look at negative rotations, although we can do either. What we are going to look at, though, is we are going to go and look at things that are going to be either positive y or negative y. And that's going to determine when something is leading or lagging. First of all, we're going to start with a reference. If we don't have a reference in whatever we're drawing, it's going to be impossible to go and keep up with what we need to go and do. So we're going to start with the reference. The reference is always going to be drawn at the horizontal along the 0 degrees. Sometimes we are going to go and have closed arrowheads for current. Other times we are going to go and have open arrowheads that are going to be voltages. We're going to start with our reference right up along this 0 over here. Because we've got that over there, we can then take a look at any other values inside of this circuit. This value over here, I see that this value is in the positive y quadrant. Therefore, anything that is positive y leads. So I can say that this voltage, we'll call this voltage J right now, voltage J is going to be leading by 120 degrees. That's how many degrees that we have out of line over here. And then if I take a look at this reference vector once again, I can go in the opposite direction and I can go and say that this reference, or this vector over here, is lagging. And the reason that is lagging is because it is in a negative y. Okay? If something's a negative, it's a lag. If something's in the positive y, it's going to be seen as a leading. You should never have leading or lagging relationships that are more than 180 degrees, because if it's more than 180 degrees, you've switched over from either your negative y to your positive or vice versa. Just watch yourself on those type of magnitudes. Okay, that's going to be our phasors. We're going to use phasors somewhat. We're not going to go greatly into them. The next thing that we're going to go and look at is going to go and be this concept of subscript notation. And subscripts are just going to be smaller letters that are going to be across here. So subscript, assembly that we might have there. Oh, I need my A over there. This would be my subscript, which is going to be talking about, my major component over here. The book over here, I'm just going to draw a big X through this, does not make a lot of sense through here. First of all, the book treats this as if there's always going to be, certain things that are positive and certain things that are negative. This is not written in stone. It is all based off of what this book is trying to do to help us analyze. Two things we need to talk about on subscript notation. We just need to talk about polarity on subscript notation. So don't even bother reading that table right now. It's not going to do much for you. What we do need to take a look at is the way that they're going to do subscripts in this book is that they are always going to be looking at doing what we call a current tracing loop. And a current tracing loop is simply going to be what happens to an electron. This I that I see inside of the center over here is what they're looking at. We know that if we've got a voltage source, in this case a battery, we've got electrochemical reaction. That electrochemical reaction is going to go and separate electrons and force them over to the negative pole. And those electrons don't like being separated from their proton that they were associated with. So those electrons are going to go on an incredible journey to try to get all the way back. And at that point, the nasty chemical rips them over to the other side of the battery. Again, they have to kind of keep repeating this until the chemical reaction peters out. But we see that the entire thing can be formed into a current loop over here. And that's what the book is talking about. The book is talking about that the first subscript always represents the end of the circuit component at which the current tracing loop enters. It says that exact sentence right underneath that table I told you to go and ignore. So for this course, they're always saying, look at where the current is entering, and then we are going to go and make that our very first subscript. Over here, my very first subscript over here as well. So I see that my first subscript over here is going to be my My first subscript over here is going to be my A because I see that it is going across. The other thing that I want you to note right now is that this point A is the same point on the circuit. Yeah, there's conductor in between those two, but A is A, same as B is B. This conductor could be a couple miles, it could be a couple inches, but it is point B on that circuit itself. And so our electrons are going to be moving, because we're always looking at the end that they enter in, the electrons are going to be moving through from here to here. The chemical moves them across to that side, and then I'm going to go across over here. At that point, it is the voltage that's generated from that potential difference that is going to force that electron through my resistive load, and then it's going to be able to make its way back to my voltage source. This is where now we can start taking a look at the subscripts. The subscripts themselves are best demonstrated with a super cheesy method, but it works for me, and it should work for you as well. It was a better method back in the day when you actually came into school. Because when you came into UFE, I would say, what is the very last thing that you put on this morning? And most of you would say shoes, okay? Shoes are the very last thing that you put on. So when it comes to my subscript notation, I'm just going to draw a couple of boxes up over here. My double subscript notation, the very last thing is always going to be this over here, my shoes. Second thing is, when you're wearing shoes, that's where you're standing, and what you're able to do then is you're able to go and use your eyeballs, and you are able to go and look at things, right? This is, kind of real basic human anatomy. The feet stand in the shoes, the eyeballs look at stuff. And that's what subscript notation is. Remember that the last thing is the shoes, and then the first thing over here is just going to be what you're looking at. We'll call that thing the eyes. So if I wanted to define my subscript notation is always defined as where I'm standing in the circuit to where I am looking inside of that circuit. I'm going to erase a whole pile of that. We're going to go and use those highlighted boxes to go and do where am I standing and where am I looking and what is my value going to go and be. Let's start by taking a look at this first one that we have right now, EBA. So EBA means that I'm standing over here. I'm standing over here. My last one, my A, tells me where I'm standing. So I'm just going to go and draw a little man wearing little black shoes inside of the circuit over there. That's where I'm standing off the last one. Where am I looking? I'm looking over here to B. So we're going to go and give some red laser eyes, and I'm going to be looking over there to B. If I was standing at this point in the circuit, looking up to there, I would say that that point over there that I'm looking at is more positive inside of there. So therefore, my value, my EBA, is going to be seen as being a positive value. Let's give it a value over here. We're going to call this thing plus 12 volts, okay? There's nothing that says it's 12 volts. We're just assigning an arbitrary value to that battery that we have inside of the system. Okay, let's go across to the next side. The next one that they said is the first subscript, once again, always represents the end of the circuit component at which the tracing loop enters. So following our current through the circuit over here, our current's traveling this way, we entered this component over here. And so when I'm looking at my value of voltage for this component, I see that the first one here is where it's entering, which means that where am I standing in the circuit? Well, I am standing on B. So I'm going to go and stand right over here. Okay. I'm standing right over there, and where am I going to be looking across? Well, I'm going to be looking across to my A, like that. So if I'm standing on B, and I'm looking across to A over there, I would say that the A point appears to be more negative. It's attached to the negative end of the battery over there, which is what assigns our polarity to this thing. So I can go and say that I have got a value from where I'm standing over there. If I'm going to look at VAB, I would say that VAB is equal to a value of negative 12 volts because it's going to be a load. It's going to drop all of my source value of voltage across it. So a negative 12 volts. Does this satisfy Kirchhoff's law of voltage? Well, Kirchhoff's law of voltage is the fact that the sum of all voltage drops is equal to my source voltage over here. I see that over here on this side, I generate 12 volts. I see that over here on this side, I drop 12 volts. Kirchhoff's voltage law is satisfied at this point. So when we're dealing with this, always take a look at the last subscript. That's where you're standing. And then go and look across to your first subscript. And then you can go and say if this is going to be a positive or a negative. I'll give you a quick example over here. What if I were to say that I wanted you to go and find me the value of VBA right now? So VBA is going to be on this side of the circuit. It's going to be a voltage drop. That's why we have a V. On this side of the circuit over here, those are going to be voltage rises or EMF generated, which is why we've got an E. But voltages across components are always going to be done with a V. If I take a look at VBA, we're just going to go and stand on the A. So we'll draw a new little dude over here. He's going to be standing on the A over here. And he's looking across to the B over here. And if I were to ask you for what VBA is going to be equal to, I'm standing here looking across to this side where it's more positive, would be 12 volts, positive 12 volts. And we see that this is just a point of reference thing. VAB is equal to negative 12 volts. And that would be if I were standing up top here on the B, looking down that way. If I were standing on the A, looking up towards the B, I see that it would be a positive 12 volts. So it's just a reference. You do this all the time with your meters at work. If you've got a DC circuit, you can go and take your meter leads and you've got a black lead, which is your reference. Guess what? Look at this. I'm wearing black shoes over here. And you've got a red lead. Look at this. We have got red laser eyesight over here. That's what your meter is doing. You've done this on a DC, or if you haven't, just do it. Take your meter, take a battery, place the black lead on the negative, and then place the red lead onto the positive, and you would read a positive value of voltage because you're standing on the negative, looking at the positive. Flip your leads around so that your black lead is now on the positive and your red lead is on the negative, and you'd read a negative value of voltage because you're standing on the positive, looking across to the negative. This is what subscript notation itself actually is. All of this chart over here makes sense in situation, but it is not always going to be for all subscripts. In fact, it's only going to be that this chart works inside of this module over here. So don't rely on this chart as an absolute. Do the better, smarter, more sciencey sort of thing where you are going to go and look at where's your shoes and where's your eyeballs looking and assess everything off of that. Okay, taking a look over here onto our next thing that we have is we've got some current tracing loops now placed into a three-phase system. And we are going to start by identifying our type of system over here. The system itself is going to be called what we call a Y type of system because it looks like a Y. And we are going to go and send from that Y system over there, we're going to go and generate voltage. Remember, this voltage is going to go and alternate. Right now it is negative, positive. But that's just because we've frozen time because it's AC, then it's going to go into positive, negative, and back, forth, etc. But right now, we're just going to look at it right now while it's got the positive over here and the negative across there because they're saying, look, we always want to do our first subscript where the current is entering. So if the current is entering at N, we're going across to A, so we're going to get this ENA. We see that we've got current that is going to go and leave out of here. Electrons that are going to get pushed out of that winding, they're going to travel across, they're going to expend their energy going through this resistor over here, and then they're going to hit this point over here, which we call our neutral, and those electrons are going to go and travel back through to here. If I take a look at my other windings, I've got two other windings that are going to go and take place inside of here. I've got my B winding. My B winding is going to do the same sort of thing. We're going to have electrons that are going to enter here. They're going to go and travel through, and they're going to come back to here, and then they are going to go and come back along that neutral. We see that we've got a complete path back through that neutral. And last of all, we are going to go and have my C. I should have actually drawn this with different colors. My apologies. Let me just change the colors over here. I'm going to draw B with black because there is a little note that you should have read inside of your binder about what the phase colors are, but A is always going to be represented as red, B is always going to be represented as black, and C is always going to be represented as blue. Red, black, blue, red, black, blue, red, black, blue. Repeat that till you've got it memorized because it's the biggest thing that's going to keep you safe when working with three-phase systems, knowing which phase you're on. Going back to my B over here, I'm going to draw black current lines for that one. I see that it's traveling out and it's traveling up, and then it's going to go and travel back along my neutral over here. And then the last one that I would have would be my C. My C is also going to go and travel from my neutral point out. It's going to travel back, and then it's going to go and hit that neutral and come back on that neutral. And it's really kind of cool because when you take a look at this, we see that all three currents, our A current, our B current, and our C current, are all going to be coming back on that neutral. And that kind of looks scary because it looks like we've got triple current on there. But we do have to remember one thing, which is that they're going to be in different directions and different peaks over here. If I take a look at my B current, if my B current is peaking, I see that my A and my C are going to be in opposite sort of directions. And same with when my A peaks, my B and C are in opposite direction. And when my C peaks, my A and C are going to be in opposite directions. So really what's going to happen in a balanced system, we're going to find out later on, is that we're going to get cancellation, actually a very low amount of current that's going to go and travel on these. That's our current tracing loops. Last thing that we're going to do is we're going to say we can take a drawing like this and we can represent it with voltage and current phasors. Just running them into these over here, we're going to be able to take those values of current and we can go and draw out our current, our A value of current, and our B value of current, our C value of current. We can draw those all out like that. They're closed arrowheads because they're current, and my voltages are going to be open arrowheads. Open arrowhead also looks like a V, just to keep them straight. We can draw them out like that as well. We are not going to go phasor vector crazy. Okay, phasors and vectors are cool and all, but they're not the end-all, be-all. It's far better just to go and trace those electrons through. We'll use the phasors and vectors at times, but we're not going to rely on them throughout this course as being, the thing. To be honest, most apprentices feel overwhelmed by phasors and vectors and subscript notation. And in most of our circuit analysis that we are going to do, we're not going to see subscript notations off of anything. We're just going to go and have values of voltage that aren't going to have a polarity, no positive or negative, because it's AC, so it's switching back and forth. So if you're freaking out because it's the very first, little bit of material that we're covering for third year, don't worry. First of all, tons of people have gotten through this. Secondly, we're not going to be using all of those at all times. We'll use them when applicable and necessary, but outside of that, we're going to try and keep it as simple as possible so that we can get the base understanding of what's going on inside of here.